This question is asking us to calculate the square root of the complex number 1 minus 3i. Because there's two square roots to a complex number, I need to know which one the question is asking for. So it turns out when you do your DeMoivre's theorem, you can represent theta in a negative fashion or a positive, but for this problem they want us to represent theta as an angle between 0 and 2 pi, which means they want the positive version. So to use DeMoivre's theorem, I need to represent my angle as z to the n. And then the right-hand side tells me how to calculate it. So z, my complex number, is 1 minus 3i, and I will plot that point in a second in this complex plane over here. And my n would be a half, because taking the square root is the same thing as raising to the 1/2 power. If you want, real quick, the intermediate algebra rule says that if you have the nth root of something to a power, call that m, then you can write that as x to the power m divided by the index. So if you want me to lay this out, our problem is the square root of 1 minus 3i, but you can think of it as that the 1 minus 3i is being raised to the first power, so that would be my m. My m would be 1, so my base here would be 1 minus 3i, the power would be 1, and my index, since it's not written, would be a 2 since it's the square root. So we could write the square root of 1 minus 3i as 1 minus 3i to the power divided by the index. So m divided by n would be 1 over 2. So that's just a quick reminder that the square root can be written as 1/2 power using intermediate algebra exponent rules. So having said that, my problem can be written as 1 minus 3i to the 1/2 power. And since I'm supposed to write my problem in the form z to the n, I'm going to do this by saying that the z, the complex number, is 1 minus 3i, and the power for which we're raising it to n is a half. So there I have the first value I need in DeMoivre's theorem. I have the n. So since I have n, to calculate the right-hand side of this, I still need r and I still need theta. To get this, I need to plot my complex number 1 minus 3i on the complex plane. So if you remember, the horizontal axis represents the real part of the complex number, and the vertical axis represents my imaginary part. So just a quick reminder that every complex number can be written in a plus bi form, and mine already is. It's 1 minus 3i. And the real part, by definition, is a, and that's 1. So I'm going to go for 1 unit on the real part. And my b, the imaginary part, is negative 3. So I'm going to go down to negative 3 on the vertical axis. And there's my complex point, 1 minus 3i, graphed in the complex plane. Now that I've done this, I can draw a reference triangle. And my reference triangle would have length 1 here, because that's the x value. This would represent as the y value, traditionally be the y value, but now it's the imaginary part, would be negative 3. And the hypotenuse would be my r. So to find the r in DeMoivre's theorem, I need to find the hypotenuse of this triangle, which can be found very easily by applying the Pythagorean theorem. So if you need to stop the video and solve this for r, you can. But basically 1 squared plus negative 3 squared equals r squared. So the Pythagorean theorem works out that r comes out to be the square root of 10. So pause the video and verify that. So once you're convinced that r is the square root of 10, I can now use that to help me find the value of theta. This is where it gets a little trickier. So if r is the square root of 10. My goal now is to get an estimate for the value of theta. Now theta can be written in a negative way like this, and that's the version your calculator is going to give you. So if you tried doing this problem using your calculator, it would give you one of the answers, but it turns out this question doesn't want that one. So your calculator uses the negative version of theta. What we need to do is find this reference angle here and think of theta as represented in a positive fashion, meaning because positive angles start with using the positive side of the x-axis and rotating counterclockwise until you hit the terminating side. This would be the positive version of theta. So normally you would take 360 degrees and subtract off your reference angle, but since we're working in radians, my theta is going to be not 360 minus my reference angle. Let me call my reference angle theta prime just to remind you. So here's theta, represented in a positive way, and theta would normally be found by taking 360 degrees, which is all the way around the circle, and subtracting off theta prime. But since I'm in radians, my theta in DeMoivre's theorem is going to be 300, excuse me, in radians, 2 pi radians is the equivalent of 360 degrees, and we're going to subtract off theta prime, and theta prime is just that reference angle and is always thought of to be positive. So to find theta prime, I'm going to set up a equation. So what's going to happen when I do solve the equation is I'm not going to get theta prime. I'm going to actually get the answer in a negative manner. So I'm actually going to get the negative version of this. If you allow me to, just let me call that A, because it actually is going to be the same angle as theta prime except negative. So if you let me just label that angle A, the tangent of that angle A is going to be the opposite over the adjacent, and the opposite side here is -3, and the adjacent side is 1. And I'm not a human calculator, so I'm going to have to use my calculator for this, but to solve this, I need to take the inverse tangent of both sides. If I was to take the inverse tangent of the left-hand side, I would get A. And then since I took the inverse tangent of the left-hand side, I would have to take the inverse tangent of the right-hand side. And my calculator is going to give me an approximate answer to this. Let me switch to my calculator. Let me clear it. I was doing some work before the video. So making sure that I am in radian mode first. So I hit mode. I'm in radian mode. Hit second quit. I'm going to take the inverse tangent. Let me slide it over. That's second tan. This is sometimes called the arc tangent of -3. And since I'm taking the inverse tangent of a negative, I'm going to get an angle in the fourth quadrant represented in a negative way. If you were taking the inverse tangent of a positive number, it would give you a positive angle in the first quadrant. But so there's my negative number. I'm going to round it to -1.25 for purposes of the video, so it's approximately -1.25. When I go do the final calculation, I'm going to use the full accuracy of the calculator. But for the video here, I'm going to call this -1.25. So A is -1.25, but as you know, we think of our reference angles as positives. You don't have to do it this way, but one way to do it is to think of now my reference angle would be +1.25. So the theta in DeMoivre's theorem here would be 2 pi minus roughly 1.25. And I'm going to get a calculator approximation to that. So it's roughly 2 pi minus 1.25. And I'm going to go to my calculator to get a better estimate for that. So if I was to take the inverse tangent of -3, that's this. Let me multiply it by -1 because the way I'm doing it, I'm going to think of that as a positive reference angle, and I'm going to subtract it from 2 pi. So I'm going to take 2 pi, and I'm going to subtract that. Now this would be my theta represented in a positive way in radians. So this would be bigger than 270 degrees and less than 360 since I'm in quadrant 4. So before I forget that this is roughly 5.034. So approximately 5.034. So you could take rounded versions of this and plug it in now to this equation. So my r is square root of 10 and n is a half. In fact, let me start writing this out. So I have the square root of 10, but it's being raised to the nth power, which is a half. And then that is being multiplied by this entire quantity. I'm going to use brackets here instead of parentheses here. It would be the cosine. So this is going to be just the imaginary part here is found by taking the cosine of n theta. N is a half. I'm going to use 0.5. And I'm going to leave theta as theta because I don't want to, it's just getting messy. So instead of putting in 5.034, I'm just going to write theta. And then I have plus I times the sine of n theta, where n is a half again. So I'm going to put in 0.5 for n. And again, I'm just going to leave theta for now. So this is what I need to type into my calculator. And I'm actually going to store 5.034, actually a more accurate answer to that, into theta on my calculator. Because theta is difficult to find on the calculator, I might just use the letter x in place of theta. So I have my answer 5.034, and because I want to use it more than once, and I'm going to do this in steps because it's kind of convoluted. The way I'm going to do is to store this into x. I'm going to hit store x, and because I didn't tell it what I want to store into x, it assumes I mean the previous answer. So here's my answer, full accuracy of the calculator. And rather than storing it into theta, because I'm not seeing theta, I guess you could use the letter O. That would be the next best thing. But I'm just going to use x for the purposes of the calculator. So on my calculator, this is going to be known as x. Don't know what just happened there, but So where you see theta in the problem, I'm going to use x in my calculator. This is just to use the full accuracy of the calculator. So now when I use x in the home screen, it's going to know it as that theta 5.034, etc. So what I have is the imaginary part here is going to be the square root of 10 to the half power multiplied to this part. Let me just do that piece on my calculator. And that would be the square root of 10. And then that's being raised to the 1/2 power, so I'm going to 0.5. And then we're supposed to take that and multiply by the cosine of 0.5 times theta. And remember that my theta really is x in the calculator. So this is going to be the real part. And the real part is negative 1.44. So as my final answer, negative 1.44 is going to be the real part. And then it's going to be plus some imaginary part times I. So I already know that the answer involves I. I didn't need to know what the sine of 0.5 theta is. And then again, don't forget to distribute the square root of 10 to the half power. So I've done this piece. I've distributed this to this and got this number. Now distributing the square root of 10 to the half power to this on my calculator. This will be a little easier now that I've set things up. I can hit second enter. And by hitting second enter, it recopies the last thing I did on the calculator. And if you look, I'm doing the same exact thing I did before, except using sine now instead of cosine. So I'm just going to left arrow over, and instead of cosine here, oops, right there, where the cursor is over the cosine, I'm just going to simply hit sine, and it's going to replace cosine with sine. And that just saves me some typing. So what I'm getting still is the square root of 10 to the half power, and that would be this piece, and we're distributing it to the sine of 0.5 theta, where theta is stored in as the variable x in my calculator. So I'm getting 1.03977. I'm not sure how many decimal places you need for this. It's roughly 1.04, but I'm not sure that that's enough accuracy to appease the Math AS is what we're using right now. So I'm not sure that's enough. So you might want to copy down more decimals to this. Maybe negative 1.4426 plus 1.039778, for example. But rounded to 2 decimal places, I get that if you take the square root of 1 minus 3i, one of the two answers is this. The other answer would be doing the same exact process, except you'd use that negative number that we got in the calculator. We would have had to go through all this rigmarole to represent theta in a positive way. So very complicated problem. It was a complex explanation for a complex problem, I guess. So hopefully this helped.